So far, the objects that we've studied have been sequences. And sequences are basically functions of n into r, which to each index, each position, associates the actual term of the sequence, the corresponding term of the sequence. But most of calculus isn't working with functions from n to r, it's working with functions from r to r. How do we extend this? How do we go from sequences to functions? Let A be any subset of R and C and point in R, not necessarily in A. We'll say that the neighborhood V delta at C, where delta is some positive number, is an interval which consists of all of the real numbers which are such that their distance from C is smaller than delta. Write this using interval notation as C plus or minus delta, if you'd rather C minus delta, C plus delta. What's the link with A? Why do we need a set A? Well, we're going to say that C is a limit point, also sometimes called a cluster point, of A if every neighborhood V delta of C contains at least one point in A other than C. Now, C is not necessarily a point of A, but it could also be a point of A. In any case, if every neighborhood of the point C contains at least one point in A, we will say that C is a limit point of A. Think about what this means. Of here a point C. Potentially, this could be A, for instance. It could be something more complicated, but it could be something like this. Now, there are going to be neighborhoods of this point C which contain points in A other than C. For instance, this neighborhood right here contains a bunch of points here that are in A other than the point C. There's other neighborhoods, though, around that point which contain no point in A. And so this point C here is not a limit point of the set A. It's written here. Whereas this other point right here is going to be a limit point of A because any neighborhood around the point, no matter how small, will at least contain some points in A here. Okay, so this one would be a limit point. This one here, not a limit point. Now the question you might have based on this drawing is, it certainly seems to be the case that if this point C is not in the set A, it cannot be a limit point. And if this point is in A, it is going to be a limit point. Is this just an accident of the drawing? Is it possible for a point C, which is not an A, to be a limit point of A? We'll do an example here. Find the limit points of the following set. Consists of all the harmonic ratios, 1 over n, where n is a positive integer. Well, do we know what this set looks like? There's 1, it is in there. Here I have 0. So I know that 1's in there. Then I have 1/2. Then I have 1/3 and 1/4. None of these points here. 0 is not in the set A, but all of these other points are. Let n be any integer. The distance between a point in A and the subsequent point. So perhaps this point in A here would be 1 over n, say, whereas the subsequent point in A would be 1 over n plus 1, say. Well, this distance is 1 over n minus 1 over n plus 1, which, if you do common denominators, is 1 over n times n plus 1. Now, this is always going to be equal to 1 over n squared plus n, which is itself always going to be greater than 1 over 3n squared. Why is that the case? Well, because 3n squared is always greater than n squared plus n for all n's. This is something you might want to show by induction, say. So now I'm going to pick a delta to be 1 over 3n squared. That is greater than 0. Remember, I've picked a specific n here to be an integer. This relationship holds for every n, but I'm interested in the one where I've picked a specific n. Somewhere here, for instance. Here's a subsequent one. So I've picked this delta here. Let's look at the neighborhood of 1 over n with this specific radius delta. Well, the only point of the set A in the neighborhood around 1 over n is itself 1 over n. This was xn. This was the next one. We've picked here a delta was 1 over 3n squared. And what we've shown in the previous slide is that the difference between xn plus 1 and xn is greater than 1 over 3n squared. That means there cannot be another point in A in every neighborhood around the point 1 over n. So what this means is that 1 over n is not a limit point of A. So we've eliminated every point of A as a potential limit point of A. What are we left with? Well, is it possible for a negative number to be a limit point of A? Say no. No negative number can be a limit point. X is smaller than 0, say, and pick as a radius half of the absolute value of x. Then the neighborhood around x of radius delta contains no points in A. Indeed, there's 0, there's a bunch of points in A, there's a point x which is negative. I pick a radius which is half of the absolute value, which guarantees that this neighborhood is entirely contained in the negative half of the real axis. And so because every single point in A is positive, and all the 1 over n's are positive, they cannot be in this neighborhood. So we have found a neighborhood around the point x, which contains no point of A, and hence x cannot be a limit point of A. In a very similar manner, if x is greater than 1, then x is not a limit point of A. What this is saying is that if there are going to be limit points, and we would say here that A admits limit points, they have to lie in the interval 0, 1, but not be of the form 1 over n, because we've eliminated the 1 over n's before. We're not saying that every point which is in the interval 0, 1 of the form something other than 1 over n is a limit point of A yet, but if there are going to be limit points, they have to be in 0, 1, but not of the form 1 over n, right? We've eliminated all the negative values, we've eliminated all the values greater than 1, and we have eliminated the 1 over n's throughout. Okay, so let x be in the interval 0, 1, but not in A, in the complement of A. I'm going to go even further than that. I'm going to, for the time being, separate those cases as either not being equal to 0 and eventually as being equal to 0. So now we'll assume that x is not equal to 0. By the Archimedean property, you can find an integer n, which depends on x, such that nx will be greater than 1 over x, which will be greater than x minus 1. And the inequalities here are strict because we have assumed that x is not of the form 1 over n, that 1 over x is not equal to some n, right? So because x is not equal to 0, 1 over x is defined. It is a positive number, and it is not going to be an integer because we've asked for x not to be in the set A. It is not of the form 1 over n, and so you can sandwich it between two integers. It might be very large if x is small. At the very least, this is something that can be done by the Archimedean. Then let's flip these around. 1 over nx is going to be smaller than x, which will be smaller than 1 over nx minus 1. I'll pick as a delta the following. It's half of the minimum of the following quantities. The distance between x minus 1 over nx, or potentially x minus 1 over nx minus 1. So graphically, here's my x, here's potentially 1 over nx, here's 1 over nx minus 1. I'm interested, I don't know where x is going to fall between these 2 points. I'm going to pick half of the smallest distance. So here's the potential distances. In this case, this would be the smallest one. I'll pick half of that. And what I'm going to show here, for this neighborhood of x, there'll be no points in A. It's sort of obvious, it's right there. And so this point cannot be a limit. The intersection of A with the neighborhood around this point, radius delta, is empty. So I found at least one neighborhood which doesn't contain any points of A. And so if x is not equal to 0, x is not a limit point. We've eliminated everything now except for 0. Still not a guarantee that 0 is a limit point, but if there is going to be a limit point, there's going to be at most 1, and it's going to have to be 0. Is it a limit point of the set A? If it is a limit point, we need to show that for every neighborhood V delta of 0, the intersection of the neighborhood with the set A is not empty. It contains points other than 0. Now 0 is not in the set A, so we don't need to say other than 0. Just need to show that it contains points in A. So let delta be an arbitrary positive number by the Archimedean property. You can find an integer n delta such that 1 over n delta is smaller than delta. Now we know that 1 over n delta is not equal to 0, and that 1 over n delta is contained in A. I mean, that's how you define A. It's the harmonic numbers, the ratios of 1 divided by integers, or the ratio 1 divided by integers. These are the elements of A. So the empty set is different than the singleton 1 over n delta, and that is going to be contained in the neighborhood around 0 of radius delta. And this is definitely what we wrote right here. Here's 0. You've given me a delta, and build the interval v delta at 0. And by the Archimedean property, I know that there's at least one point in here, which is 1 over n delta. Now, there's more than one. All of the subsequent points would also be in there, but there's at least one. And so the intersection of v delta 0 with A is not empty, and it contains something which is not 0, and hence, and this is true no matter what delta I've picked, so you would conclude that 0 is a limit point of A. In fact, it is the only such limit point. So, how do you feel about this example? How much work was it, using the definition of a limit point, to identify the limit point of the set A? It's a fair amount of work, and look, A wasn't the most complicated set you can think of defining. You think you'd be up to computing limit points by hand, such as it is every single time? We'll see in the next videos that there's a nice theorem that links limit points. Now you might have been wondering why we call them limit points, and actual limits of sequences. And then you'll get your answer. This is why we call them limit points.